We all learned it, right?
Mm-hmm.
A tiny hard electron spinning around a central nucleus, like a miniature solar system. It's a comforting image, very intuitive.
It is, yeah. And it serves as a valuable stepping stone, in understanding the atom. But this classical planetary model faced a fundamental paradox, a problem so significant it suggested something was, well, deeply wrong with our understanding.
Right. And that problem, according to the old physics, was pretty simple. An accelerating charged particle, like an electron moving in a curve around a nucleus.
Exactly.
It should constantly radiate energy. You should basically be a tiny radio transmitter.
Precisely. And as it radiates away energy, it should lose speed, its orbit should decay, and, well, it should rapidly spiral inwards, crashing into the nucleus.
We're talking fractions of a second.
Tiny fractions of a second for an atom to just collapse.
Which means, classically, atoms shouldn't exist. They should be fundamentally unstable, dissolving almost instantly.
Yet here we are. The world around us is built of atoms, and they are incredibly stable. This glaring contradiction between classical physics and, the observed stability of matter was one of the biggest mysteries heading into the 20th century.
And the sources we're digging into today point to the radical idea that began to resolve this. The electron isn't just a particle. It also behaves like a wave.
A matter wave, to be precise. This whole deep dive is really dedicated to understanding how this revolutionary concept, the electron as a wave, not just a point, how that solves the puzzle of atomic stability and explains why electron energies within atoms aren't continuous, why they exist only at specific, discrete levels.
Right. So let's just zero in on that classical puzzle one more time. The planetary model, electron accelerating in orbit. Why exactly must an accelerating charge radiate energy according to that old physics?
Well, classical electromagnetism is quite clear on this. Anytime you change the velocity of a charge, either its speed or its direction, it experiences acceleration. And accelerated charges are sources of electromagnetic radiation. Light, radio waves, X-rays, you name it. Think of how alternating current in a wire creates radio waves. The electrons are accelerating back and forth.
Okay, so an electron constantly changing direction in orbit is accelerating.
Definitely.
And therefore must radiate energy away classically, which, like you said, leads to the spiral of doom. This wasn't a minor issue. It sounds like a complete showstopper for that model.
It absolutely was. The mere existence and persistence of atoms defied this fundamental prediction. Something was missing, something profound about how matter behaves at the atomic scale.
And that's where the idea presented by Louis de Broglie in, 1924 comes in?
That's the one.
He hypothesized that wave-particle duality isn't just for light. It applies to all matter. Electrons, protons even. Well, even us, theoretically.
Yes, exactly. Suggesting that an electron isn't just that tiny, hard sphere, but is also associated with a wave, a matter wave, that's kind of spread out through space, not localized to a single point.
And the sources point out there's a specific relationship de Broglie proposed between this wave and the electron's particle properties. Its wavelength is inversely related to its momentum.
Precisely. A faster electron, meaning higher momentum, would have a shorter wavelength.
Right.
A slower electron, less momentum, a longer wavelength. This wave nature is the critical piece when we consider how electrons behave when they're constrained, like they are inside an atom.
Okay, so to understand how waves behave when constrained, we first need to maybe touch on a fundamental wave property, interference.
Right. Think about waves on water, maybe from dropping 2 pebbles in a pond.
Okay.
Where crests meet crests, they reinforce each other, making the wave bigger. That's constructive interference.
And where a crest meets a trough, they cancel each other out, leaving the water flat. Destructive interference.
Exactly. Waves adding up or wiping each other out, depending on their relative timing, their phase.
Okay, so now what happens when a wave is confined? Like the sources use the analogy of guitar string tied at both ends.
A classic analogy, yeah. When you pluck it, the wave travels down the string, reflects off the end, travels back, and interferes with itself.
But the sound isn't just random noise. You get specific musical notes, stable vibrations.
You get standing waves. And the key insight here is that only certain wavelengths of vibration can actually persist stably on that string. Only those waves where the reflections interfere constructively with the original wave, resulting in a pattern that appears to stand still. You get points of zero movement, nodes, and points of maximum movement, antinodes.
So only wavelengths that fit perfectly between the fixed ends, like having a whole number of half wavelengths fit the length of the string.
Exactly right. Those are the allowed standing waves, the fundamental note in its harmonics. Any other wavelength you might try to introduce, any wave that doesn't fit that condition will interfere destructively with its own reflections. It just quickly fizzles out. It can't maintain itself.
So it's like survival of the fittest wave. Only patterns that reinforce themselves survive this internal interference.
That's a really good way to think about it. Now let's extend this idea to the electron wave, which is confined within the atom by the nucleus's electromagnetic pole. It's not a simple string, obviously, but the principle is similar. The wave is confined and interferes with itself.
So the electron wave isn't just a point moving along a path. It's this spread-out wave filling a region. And it must interfere constructively with itself to remain stable within that region.
Right. For the electron wave to exist stably, persistently within the atom, it must form a standing wave pattern. The condition, especially if we think about a simplified view like Bohr's old circular orbits, even though we know it's more complex, is that the circumference of the path, the space the wave occupies in one cycle, must be an integer multiple of the electron's wavelength.
Okay, so if you imagine the electron wave kind of wrapping around the nucleus,
Yeah.
the total wraparound distance has to be exactly one wavelength or two wavelengths or three.
Yes.
It has to close on itself perfectly in phase.
Precisely. If an exact whole number of wavelengths fits, when the wave completes a cycle around the nucleus's influence, it meets up with itself perfectly aligned crest meeting crest, trough meeting trough. This continuous self-reinforcement creates a stable, self-sustaining, standing wave pattern.
And these stable patterns,
Yeah.
they correspond to the specific discrete energy levels we actually observe atoms having.
Yes. These are the allowed quantum states. But what if the wavelength didn't fit perfectly? What if, say, 2.7 wavelengths would complete the path?
Well, the wave wouldn't line up. When it came back around, a crest would meet a trough or something like that.
You'd be out of phase. On every single cycle, the wave would destructively interfere with its own beginning, its own trailing edge.
And it would just annihilate itself,
Yeah.
dissipate. It couldn't stick around.
It couldn't form a stable pattern. A wave pattern that doesn't fit the boundary conditions imposed by the atom's confinement just cannot sustain itself through constructive interference. It undergoes rapid destructive interference and simply cannot persist as a stable state within the atom. These are the forbidden states.
Okay, this is the a moment the sources really drive towards, isn't it? This standing wave condition directly explains why electron energy in atoms is quantized. Why it's not a continuous spectrum, but only specific values.
Because the electron's energy is directly linked to its momentum, right? And its momentum is linked to its wavelength via the de Broglie relation. Higher energy generally means shorter wavelength. Lower energy means longer wavelength.
So since only certain wavelengths are permitted to form stable standing waves within the atom specifically, those that fit an integer number of times, only the specific energies corresponding to those allowed wavelengths are possible.
The electron wave simply cannot exist in an energy state that would correspond to a wavelength that doesn't form a stable standing wave pattern. Such a wave would essentially self-destruct. The atom's structure, the nucleus's pull, acts as a kind of boundary condition that filters out all but the stable wave pattern.
Okay, that makes sense. And the familiar shapes of atomic orbitals, the SPDF blobs you see in chemistry textbooks, the sources explain these aren't just random probability clouds.
Not at all. The sources describe these as basically three-dimensional representations of these stable standing wave patterns. They are maps showing the amplitude of the electron's matter wave in 3 dimensions.
So the shape indicates where the electron wave's intensity is highest,
Right.
which corresponds to the probability of finding the electron particle in that region.
Exactly. The simplest stable pattern in 3D, kind of analogous to the fundamental mode on a string, is spherically symmetric. That gives you the Essig orbitals. The sources probably mention the one's orbital being the lowest energy state, the simplest spherical wave with no nodes, no points where the wave cancels itself out internally.
And the 2's orbital is also spherical, but it's bigger and has a node inside, like a shell where you won't find the electron.
Right, representing a higher energy standing wave. It has a spherical nodal surface where the wave amplitude is 0. It's much like higher harmonics on a string have more nodes along the string.
Okay. What about the dumbbell shapes then, the p orbitals?
So they appear from the second energy level onwards, and they represent more complex standing wave patterns in 3 dimensions. The dumbbell shape arises from a wave pattern that has a nodal plane passing right through the nucleus.
A plane. So for a, say, 2px orbital, the wave is strongest along the x-axis, but it cancels out completely in the plane made by the y and z axis.
Precisely that. These more complex shapes, with their specific nodes which can be planes or cones, are simply the geometric requirements for a stable, self-reinforcing standing wave of that particular energy and angular momentum to exist within the 3D potential well created by the nucleus. The sources link the number and type of nodes directly to the increasing complexity of the wave pattern allowed at higher energy levels.
And D and F orbitals are just even more intricate.
Yeah.
Higher energy standing wave patterns with even more complex arrangements of nodes.
Exactly. They are the necessary shapes for those specific waves to achieve stable, constructive self-interference in 3 dimensions within the atom. They aren't arbitrary. They're the unique geometries demanded by the wave nature and the confinement.
So, pulling this all together from the sources we looked at, the bizarre quantized world of the atom, the fact that electrons only occupy specific energy levels and exist in these strange orbital shapes.
Yeah.
It's not just a set of arbitrary rules handed down by quantum mechanics.
No, it's presented as a direct logical consequence of the electron being a wave confined within a small space. Just like a wave on a string or in a cavity, it has to obey the rules of interference.
And the stable energy states and orbital shapes we actually see are simply the only wave patterns that can successfully interfere constructively with themselves and persist within the atom structure. Every other potential wave pattern would undergo destructive interference and just can't exist as a stable state.
What we observe in the atom is essentially a consequence of survival of the stable wave pattern. And this fundamental insight isn't just abstract physics. It underpins our understanding of chemical bonding, material properties. Really, why the physical world around us doesn't just dissolve.
It solves that initial paradox, the collapsing atom problem, that the stability isn't assumed, it actually emerges naturally from the quantum nature of the electron.
Exactly. The atom exists in the form we know because its electron waves are constrained and must satisfy the conditions for forming stable standing waves.
So here's maybe a thought to leave you with. The reality of the atom, its structure, its specific energy levels, its orbital shapes, isn't everything that could potentially exist according to the fundamental rules of quantum mechanics.
Right.
But only those quantum patterns stable enough to persist against constant internal self-interference. What does this idea of survival of the stable pattern imply about the fundamental nature of reality, perhaps even beyond the atomic scale?